Welcome to Model 7, Prognostic Health Management. In this model, we will take a look on the introduction of PHM, the concepts, the common PHM model that's enabled to predict the remaining useful lives based on equipment condition, operational condition, that is detected based in sensors, remaining useful life, state of health, and in the end, we'll have an example of our Arule software case study. So, as already discussed during this training, it's very important as a first step to understand all the the maintenance concept, the difference between corrective maintenance and preventive maintenance, and the different types of preventive maintenance, such as scheduled maintenance and predictive maintenance. In addition, depends on the impact of equipment failure downtime and the frequency that failures occur that directly affect the life cycle cost, the operational cost, different strategy of maintenance need to be implemented. So in the past 5 years, the more technology was implemented and developed in order to have not only conditional based monitoring, but also based in this conditional based monitoring, the softwares implemented as part of prognostic health management enable to predict the remaining life of physical assets as well as the stage of health, and that's a very important advantage for maintenance that gets alarms and focus on critical issues, and they can input and implement preventive action. So the strategy in the end is very important. So this type of technology will be implemented depends on the impact of the failure, of course, if they have a high impact on downtime or cause a major accident, and it needs to be implemented and depends upon as well the frequency and the cost. It needs to be implemented. So the usual step that we consider before prognostic health management was the online monitoring. And online monitoring is not prognostic health management. So prognostic health management is more than that. So let's take a look on the concept of online monitoring. So here, basically, we have equipment, a compressor. Then this compressor have some sensor installed around the compressor in different areas to detect vibration, to detect temperature. Basically, vibration is one of the physical parameters that impact in different components and can trigger failure. So basically, what's going to happen is such a sensor will be associated in a data interface system that will go to a server, and then this server will bring such information in graphs about the level of vibration that such a compressor are facing during operation, and whenever that's achieve an upper level, so the team maintenance and operations need to take some actions. Usually the maintenance engineers are assessing such assess information, and then of course whenever some information gets and shows that the equipment achieved the top of vibration that can trigger some failure, they by itself need to assess if it's critical for the equipment, and if and but he needs to assess by itself, for example, the state of health of the equipment when achieves the such target and the remaining life. So that's the difference between the prognostic health management and maintenance, because prognostic health maintenance will tell this information automatically for the maintenance engineer, will bring in an alarm and show depict in their screen all such information. Then that's enabled them to take a faster decision and prevent failures. So just to clarify and to focus, emphasize the difference between the online monitoring and the prognostic health management is that prognostic health management will, of course, um, make the diagnostic automatically based on online information. This is one point. That means it will provide the information about the level of state of health of equipment, as well as to predict the remaining life. And of course, such technology enable to trigger some alerts in different equipment here, and this alert will be able enable that this maintenance specialist take action faster and have information, clear information, and needs then to prioritize the new issues that comes out in daily basis. So before going in deep details about prognostic health management, we need to understand that there's not only one method of preventive maintenance that can be applied in a specific equipment, of course, and in addition, in the context of maintenance system management, there are more than one tools that come together to the system. So, of course, we have here the online monitoring and the detection, the state that's enabled to predict the state of health, or even clarify what is the state of health predicted in some in the prognostic health management. But of course, you are able to look in details about the signals come from the sensor, the critical sensor, to assess better such information. In addition, this prognostic health management system, there are also all the maintenance plan. In this maintenance plan, is triggered by schedule maintenance. There are preventive maintenance based on schedule that comes from RCM, comes from RBI inspections, as well as for other inspections that is defined for the RBI and set up in a CMMS system in the very beginning of operation in plant, and then later on this plan is constantly updated. So in the end, such a prognostic health management, when they trigger some issues based on the sensor detection and predict the remaining life, such information will also in the end be input as schedule maintenance and will be part of a maintenance system management. And the last evolution that we can have is that such prognostic health management and maintenance planning in the end is part of the asset management system. We'll speak that later on. So now let's focus on prognostic health management concept. Is a simple concept. Is a, actually is an evolutionary concept. So here we have the conditional based data. So that's the first step, that you have conditional based monitoring. So we need to have a sensor linked to some equipment to detect the physical parameters such as vibration, temperature, uh, rotation, and some physical parameters that can trigger failure. In case of electrical electronics, will be temperature, voltage, the ones that trigger failures. And then, based on such information, we are able to link such sensor information to a computer, a device. And then that will be need a software so to calculate the and make the prognostic of remain useful life and states of health. And then, of course, the manager will have the information to anticipate this failure. So here we can see the condition data that comes out. So these data are normalized. Then the prognostic information remaining useful life based in time, based in different inputs information that can be temperature, can be pressure, can be voltage, can be rotation, can be vibration, for example, will be demonstrated the picture in a screen, as well as the stage of health of the equipment based on the condition. And the main issue here is when the such physical parameters, pressure, temperature, vibration, rotation, go over the operation limit. So, and that's the main issue, and that's why important prognostic health management is. Because when the equipment operate under their operation limits, the remaining useful life is have a high chance to be as same as the one predicted by reliability analysis by based on historical data. But when such parameters go over the operation limits, then such parameters, pressure, temperature, rotation, start to influence on the reliability of equipment and reduce the remaining life as expected on the very beginning. And then that's why it's very important to have the prognostic health management. So again, we have one sensor data that goes to a computer solution, a software that is the prognostic health management that links such information and based on some models. So we define which kind of models that need to have that. So basically, the Kalman model is a function that have different regions that we plot some points, and then those points are the points over the limits of operation, and then based on such points in the relation between the physical parameter and the time is will be able to in the end predict the remaining life, and when such a remaining life achieve the limits of operation that will trigger a functional failure regarding some parameters. And then the advantage you have that is the such solution different from the condition-based monitoring calculate all this prediction automatically, and then as much as information faster comes out from your system and enable maintenance specialists and technicians take decision faster, better and faster solution can be done. So here, this slide shows example of sensor system. So as I mentioned before, you have the final output is that the safe state of safety, states of health of your system and remaining useful life. But of course, you can always look upon the signal and try to manipulate to clean the signal and follow up and look the signal in detail. So the signal can be a temperature, it can be a pressure, it can be rotation. Depends on the failure mode that you are defining. So, as I mentioned before, in order to transform such signals, such information that comes from sensor to a prediction model, it's necessary to have a model to support that. Then the whole idea in prognostic health management that we are presenting here is based on Kalman model. So the Kalman model concerning what is the possibility to have different prediction of the time in operation, that is the remaining time in here, and that's live consumption in percentage. So the idea is to show what has happened if we operate over the operation limits, and then this useful life predicting here can be worse, and that's the case of degradation, or even better if some new conditions are input in the system. So usually we'll get in this case here that is the worst case that demonstrates some degradation in the system, and then that is the main issue when we have the system operating over operation limits defining design. So when your system have a higher vibration than defining design for the operation of such equipment, a compressor, a pump, what's the effect of the impellers, what's the effect of the other components when in bearing, for example, when such equipment have a high temperature sensor operating over the temperature limits, and what is the remaining life predicting. And it's very important that is such a model is updated online. Whenever comes out new information, the remaining life will be updated automatically. So what is the concept behind a Kalman model? So as I mentioned, we have a function that will predict when we have the functional failure, and based in this limit that is defined in some parameters, we are able to see the remaining time. And then of course this function have three regions you need to set up these 4 points, the usual points, but also the points, three other points that achieve the limits of operation that you trigger a functional failure. And then, of course, based on it, the model, when as much as coming input data or temperature or vibration or rotation uh, or other parameters. So this line here, this function will starting to adapt, and he and is reconstructed again and can get different directions, such this one that will predict the remaining life before the expected, or even some cases after the expected. So that is the, the, the issue relating that. In order to do that, we need to have the two inputs, in fact, for this column model. The first one is to have a baseline for these 4 points that is expected for a specific profile concerning equipment failure modes, physical failures, and parameters such as temperature, vibration, and related to some specific percentage of lifetime, remaining lifetime. So based on it and based on the real input data, that's the system, the software solution for prognostic health management will be able to predict the reliability. So let's take a look on here to have a clear understanding. So we have here the first point, and this first point is operating exactly in the limit in the operation conditions. So in this case, the remaining useful life is as expected and as predicted by reliability, considering the equipment operating condition, normal condition, so there will be no degradation. And in this case, of course, we will get such equipment operating. The remaining life will be in the end will be what was predicted, because this there's no any other the equipment operated during all this time under operation limits. So let's consider that here is temperature, the sensor operating and a maximum temperature of 40 graus Celsius. So during all this time, the operation during 4 graus Celsius is that operation condition, though there's no um, changing in this remaining useful life. But in some cases, this sensor will operate in a temperature condition over this 40 graus Celsius, 45, 50. So as long as this point is starting to come out here, so this curve here will automatically change on time. So let's take a look on here when we have the second point in temperature, and this second point already trigger the temperature of the sensor. Let's consider the sensor as an example in a temperature over the operation limit, and when it's over, of course, cause some degradation. Then automatically, when we have 2 points, this curve is adjusted, and now is predicting smaller remaining life than expected in the beginning. So in the first point, as we presented, we have this useful remaining useful life in here, as was predicted in the beginning for the reliability studies. But uh, after during this operational time, there was some period of time that this system operating in this temperature above this 4 graus Celsius. Then now the remaining life is not the one that was predicted under usual condition, but it will be lower. And then, of course, as much as information we have, as much such equipment, in this our case sensor, have this peak of operation above the operation limits, shorter will be the remaining life. And then we can see here, after many points, whenever comes out to 1 point, the curve is adjusted, and then in the end, the prediction is a short period of time. The advantage to have such prediction is that in real life, we are expecting to have this remaining life, and then based on it, we plan some intervention in some period of time before we expect that this failure happen. But what's happened is, as long as the equipment operates in a condition over the limits of operation, then these periods, it will remain life is starting to be shorter. And basic of a reliability models, we are able to predict this effect only after the failure. So, but the case here is that the equipment did not fail. So the equipment has only effect of a worse condition, but the remaining life is reducing. Then the advantage to have this model is that I'm aware about that, and that's now the remaining life is shorter, almost 50%, because this sensor operating in many times in higher temperature than operation, and then I can make an inspection very accurate now, not in this region as usual as defined in the very beginning, but consider all these effects in the proper time. So if I what I'm telling you is that if I just consider the first prediction and not apply prognostic health management in this case, so I will expect to do an inspection here, but the failure will happen here, what they are demonstrating. And then, of course, that will be a corrective action. Some in sensor case, in most of cases that will not be critical, but in some device, some equipment can be critical. You can have an equipment shut down, for example, in case of compressors. We have a lot of problems issue triggered by vibration. Then, of course, we are if we have a prognostic health management, we will be able to have the our remaining life prediction updated based in all along the operation time, and whenever some condition, the compressor, for example, operates over the usual operation limits, such a remaining life will be updated and automatically. So that is the end advantage. And of course, this prognostic health management alert in the system, that's a new point over the limit comes out, and a new prediction come. We have, and there will be a new prediction for remaining life, and then that will be a dynamic information, and the maintenance group will have a dynamic maintenance plan because updated constantly based on such information. So, as I mentioned before, we need two type of inputs. One input is we need to define basically the model that are the regions that we consider. So I'm talking about this region here. So we need to define, for example, considering temperature for a sensor, we need to define three regions, 4.3, at least 3 points, the limits and the destruction limit here for that trigger, the functional failure and the operation limit. That's the beginning. And between these 2 points, we need to define, of course, two other points that are the regions that the software will use to adjust the prediction. So is what we have here. We have A0, A1, A2, and 3. So in percentage, and in the end, we have the temperature that we consider temperature 1, 2, and 3. And then that's very important setups to adjust this function. And in the end, of course, we will have this prediction of prognostic health management of each solution, and what's happened, the remaining life prediction in the beginning, if it will be after or before the prediction time. So basically what we have is the remaining useful life. So here is the time in weeks. Here are the parameters that are captured along the time. And then this line in blue is the theoretical function that is defined based on this profile. And then, of course, based on the point that comes out, we have different prediction. Another type of information is the states of health. So states of health demonstrate that this equipment have 100% in the beginning until this operation time, and then when you start to come new points that the system operates over their operation limits, these states of health is starting to decrease along the time. And then we have the state of health in terms of percentage, and for each percentage we have in the end the predicted in the end we have the is will be related to the remaining life of the equipment. So here we have an estimate curve that's based on the point is in red, and the initial one in blue is what we have. So remaining useful life is the same. So we have different points and the lifetime that we have in the end. And of course, we have the blue line, the ideal one. And then you can see the adjusted file, the adjusted one in the black one that shows the remaining useful life in the end. So let's take a look at an example to understand how this Arule solution works. So basically you have your system operating, let's say in some temperature that is minus 1.5. So let's take is 1.5 generic one. We can have whatever uh, parameter in here. We can have pressure, we can have rotation, or we can have a voltage. So let's to make it clear and a better understand, let's consider now this 1.5 multiplier for 10. So we have minus 15 graus Celsius your sensor is operating. Okay, so that's the very beginning. If you look on this temperature, you have in the very beginning the remaining useful life as 1000 days. For the sensor you have 100% of a state of health, and there is no remaining useful life degradation, so you still have this 1000 here expected. So as long as we start to have additional points, so now comes out your second point. So you still in the same level in minus 15. Let's consider 1.5 multiplied per 10. 1.5 multiplied for 10, you have minus 15 graus Celsius in here. You now still have the same similar very small error on your prediction 1 to 1050, and then you still have 100% remaining life. So that's happened because that is the limit of negative operation if you have minus 1.5 in here. So as long as you start to have points above this minus 1.5, so and that is starting to happen now, you still have in the third, when the time is 100 days, you still have minus 1.5. So you working in the limits of your operation conditions, so there's no change in remaining useful life. So you still have 1000 days because the condition is of such equipment is operating under the limits and there's no degradation. So and now let's start to look when you have lower points. So that is starting to have the issues, the points that now is starting to have above your operation limits. So your now your remaining useful life is lower than 1000 days, is because you have 1 point here. It's minus 1.45. That's degrades your life, your remaining life to 1000 to 900 something here. Now you do not have more this stage of health of 100%, but you still have a very high that is 95% or higher. Then you come a second point. Then again, now your remaining life is 800 days and not more 1000. And now you have at the second point here. Pay attention that this regional plot, you have three regions that you set up, but your point is coming this first region here. Then the next point comes out, and then when these points is starting to come over this operation limit, that's your physical parameters. What's happening is your state of health is decreasing because you now you starting to have times that your system operate, your equipment operating over the operation limits. So your state of health now is not 100%, is 60%, and your remaining life now is not more 1,600. Then you can see how much you still have for operating. So you still have sometimes that you achieve your final remaining life. So then a new point comes out and your plot is starting to be done. Your prediction of remaining life is being done. So if you look on this graph, he's completely uh, under the first expectation. So let's go. All the points comes inside in this function here. That's just to demonstrate. Then, as much as you operate over the operation condition, your state of health decrease. Then, as well as your remaining life now is lower than 1,000. And then, of course, the error of the initial prediction, the final prediction is starting to range in here between 1,000 and 1,100. So again, this is 1,100 the prediction. This is 1,100 the final prediction after all your points. And in the end, when you achieve 1,100, you have zero of state of health. And of course, you can see here the difference between your error for an initial prediction to the final prediction. In the end, your remaining life was 1,100. So that's the best case scenario. But let's see example two, where, and that's the usual one, that's the plots, the real information that comes out from the sensor do not will fit 100% on of your profile, model profile that you define. So in this case, you have in the end the final prediction periods before this 110. So the remaining life is 100 days before is expected. And that's very important, this information. As long as you're starting to input the points, this profile is starting to modificate and demonstrate to you that you have expected life not only 1,100, but now you have in 1,000. So before you expected. If you are able to get such information, such prediction, you are able to anticipate that the failure will occur before it is expected, and then of course, harder to do a preventive maintenance in 1,000 or a little bit before 1,100. You do around 1,000, and then you avoid the equipment shutdown, and that is the information that prognostic health management gives to you. And of course, the opposite case is the best case scenario, where you have very good points now of inputs, and then your equipment will increase, is under, can even operate in a better condition. Then this estimation life can be longer than expected. So that's 1,100 that was expected in the beginning was postponed for 500 hours. And that's also save some inspection, preventive maintenance, and replacement of the equipment, because you are not doing something that was scheduled for 1,100, but you're doing 1,500 or before. So you postpone, you have more time to do another type of maintenance in other equipment, because you have the updated prognostic health management. So the conclusion is that when you have your asset managed PDCA cycle, you have as one of the most important information is to monitor and detect problems before it's happened in your physical assets. And then one of the main issues is to, whenever some issues comes out, and basing usually in inspection, non-destructive tests that you perform along the time, of course, you can predict some degradation, put in the failure report, or even incidents and accidents or failures that occur. You put in the failure report, you prioritize the risk, you propose corrective actions, and together with some management of change, you assess all the such issues in cost benefits, and this will be part of your performance assurance flow that will need to be in line with your strategic asset management plan. And of course, You always constantly perform your KPIs based on online monitor, and whenever you need to mitigate the risk, you look upon your KPIs as well to see the effect. The point is, you need, based on such approach, based on inspections and non-destructive tests, you need to start to see some degradation and get some points to be able to predict the remaining life of such equipment. But when you implement the prognostic health management, you have information online. So whenever some equipment operating over the operation limits, will be possible to predict the remaining useful life as well as the stage of health of equipment. And then you have such information updated on time that's enabled to be more preventive. So thanks for your attention. Uh, that was the objective of this model, to present the concept of prognostic health management. This solution is being implemented in the Integrity Pro, our solution for asset management, to enable that you follow up all the, of course, ISO 55001 elements, as well as to have a very preventive asset management system that are able to predict and to avoid error, even to implement actions along the process without any specific measurements of system health, but based on prognostic health management concept.